you're welcome to come to SLAC. This is amazing to have this auditorium full, and it's very nice because the speaker today, you're gonna love it. He's such a cool guy. Before I get to introduce Jonathan, there are two more things I have to remind you. If you take an airplane, you know what it means, right? There are no oxygen masks here, so don't worry about it. So the two exits on the back, two exits here in case of emergency, and you're saying, well, what if I have an earthquake? Well, we did have an earthquake here during a public lecture, and everything went fine. So do not worry, we already practiced. So what I ask you to do, if that happens, you have to be calm, you have to be quiet, and we're gonna guide you to the exits, and everything will work very well. So don't worry about it. We know how to handle situations like that, okay? So another thing that I wanted to say is that if you have a pen and a pencil, now it's a good time to take it, because you have to write down this date, important date, May 12th. What is important on May 12th? Does anyone know? Go ahead.
Angels and Demons.
That's May 15 on the movies. What is it with you? But on May 12th, you may have questions such as, does antimatter really exist? Do scientists use giant machines to produce antimatter? For what esoteric purpose, if that exists? Is there an underground laboratory complex deep beneath the French-Swiss border? Is truth stranger than fiction? If you want to know more about the science behind the scenes of the movie Angels and Demons, we're going to have a very special lecture here on May 12th. And that's going to be really, really cool. The speaker is also another one of these great guys. So come back, same time, 7:30. And if you know where to go, the SLAC website. If you don't know where the SLAC website is, Google it, SLAC. Public lectures, you'll find it. And May 12th, hope to see you again. Come early, because I think it's going to be crowded again. All right. So let's get to the main feature of the evening, which is our speaker, Dr. Jonathan McKinney, theoretical astrophysicist, a colleague at the Kavli Institute for Particle Astrophysics and Cosmology here at Stanford SLAC. Jonathan got his PhD in physics, University of Illinois at Urbana-Champaign in 2004. And he's a smart guy. What he did, he used these very fancy supercomputers to calculate Einstein's equations. And when he solved them, he actually figured out how spinning black holes feed, grow, and produce jets. If that all sounds weird to you, he's going to tell you more. But after that, what he did, he got a fellowship, a theoretical and computation fellowship at Harvard. And he has been working there for these years on what powers black holes and neutron stars. And then we are very fortunate to have him here in a prestigious fellowship called the Einstein Fellow since 2007. Ever since, Jonathan has been working on how massive stars go supernova, boom, and sometimes produce gamma ray bursts. Tonight, he'll be telling you everything you want to know about black holes and a little more. After that, we're going to have some refreshments and there will be some time for questions, okay? There will be some astrophysicists in the audience wearing these very sexy hats, okay? So you can ask them questions if we can find them, because to my knowledge, they disappeared into a black hole. I don't see anyone available, but we'll figure that out. So let's just give a warm welcome to Jonathan before I get started.
Okay.
it sounds like I have noise. Thanks, Eduardo, for introducing me. It looks like a really good crowd tonight. I'm very excited. I hope that by the time I'm done, I will have kind of had you learn some things about black holes that you never knew, and also kind of demystified black holes and demystified some of Einstein's relativity and the nature of space and time. So black holes to scientists are like a cosmic boogeyman. They're extremely scary objects. The reason why that is because inside a black hole is all the mysteries of the universe. All the secrets of the universe are hidden deep inside. The problem is that black holes are also extremely unnerving. We really hate them at the same time. The reason is because all these secrets are hidden inside what I'll eventually describe. It's called the event horizon. This thing hides all the secrets. So this is a really kind of sticky scenario. Before I move on, I want to talk a little bit about some basic ideas that you'll need to understand in order to appreciate the rest of the talk. They're really, really simple ideas. The basic first idea I want to make you remember or have you know is the nature of light. Light comes in all sorts of frequencies, sort of how fast it vibrates, all the way from radio waves, just like on your radio that you have in your car, microwaves that heat your food, infrared that we feel as heat, visible light that we see, and then there's ultraviolet light, which we try to get rid of. We don't want to have it hit us. And then there's X-rays, like in dental's office. And then finally gamma rays, like when nuclear reactions occur. And most of the things that are related to black holes happen at these very, very high energies. So that's one of the things that makes them really interesting, is that they are very high energy objects. They also produce all sorts of other kind of interesting emissions. Now, the most important thing for this talk about light, apart from the fact that it has all these different kinds of light, is that it has a very fast speed. It's ridiculously fast. Everybody knows this. It's like 186,000 miles per second. It's extremely fast. Well, that's kind of confusing. It's a big number. How do you kind of wrap your head around that? One way you can do that is, it turns out that light will go around the Earth completely 7 times by the time it finally goes 1 second. This is a huge, huge number. So this is equally amazing as fast that light is. Equally amazing is the fact that there are huge distances in the universe. It turns out that even though light is really fast, these distances are so huge it makes light look small and slow. So we have to sort of calibrate our understanding of the universe by introducing what we call the light year. And this is simply the distance light travels in a single year. Further, we'll even go further than that. The universe size will even include things like millions of light years and billions of light years. So these are really tremendous distances. The other thing that you'll need to know, sometimes I'll introduce a notation that looks like this. It says 4 multiplied by 10 to the power of 5. All this means is that I've taken 4 and then multiplied it by 10 5 different times. Another way to look at it is I have 4 multiplied by 1 with 5 zeros. So all this really does is it kind of counts the number of times you multiply by 10, or you can think of it as how many zeros are there after the number. The other thing I want you to remember or know is that there's a difference between stars and planets. Really basic idea, not too hard. And here I show several panels going from 1, 2, 3, 4, 5, 6. And each time I cross a panel, I've taken the last object and put it as the smallest object. So this kind of gives you an idea of the scale of stars and planets, their size. What's interesting is probably the ones I've highlighted with these little words here. And in particular, the sun, as we know very well. And the sun is going to be useful because not only is it interesting itself, but it also is a reference point for all their stars. So we'll call this one solar mass. It's a single star mass. And we'll also say it has one solar radius. So when I talk about other stars, for example, Sirius, it actually has about 2 solar masses. And that means it's twice as massive as the sun. And it has about twice the radius. Now, the interesting thing about Sirius is that it's actually the brightest star in our sky. It happens to be quite close, and this is the reason why it's the brightest star in the sky. It's also, Sirius stands for dog star. And it's related to why we say the dog days of summer. Now, it turns out that another interesting guy is this guy named Betelgeuse. Betelgeuse, as you can tell from these panels, is extremely massive, and it's extremely large. What makes it interesting is that it's about 20 times as massive as our sun, and about 1,000 times bigger, and maybe 1,000,000 times brighter. But it's so far away. And what's also interesting about it is that it's actually the first star that we ever observe the surface of outside our own solar system. So this really makes it exciting. It's really big, but quite close. Finally, the last star I'll mention is this guy. This is a real monster. This is called VY Canis Majoris. This star is the biggest known star in the universe that we know of right now. It's about 2,000 times bigger than the sun and about 100 times as massive. This is a real monster. And we'll use these kind of guys to understand how black holes form. And in particular, only these massive guys, these ones that are really monsters, are the ones that will eventually become a black hole. You really have to start off with something really monstrous to make something like a black hole. Before I move on, I want to sort of break the ground between us and say, well, maybe I don't know what you know about black holes. Maybe there are some myths that you think about black holes, or maybe you don't know some interesting facts that may help you appreciate the rest of the talk. And so I'm going to go through and actually ask you, the audience, to raise your hand if you believe some of these things are true or false. So the first thing I'm going to ask is, light bends due to gravity. How many people believe, raise your hand if you believe that's true. All right, can you now raise your hand if you believe it's false? We got some skeptics there, that's good. So it actually is true. It turns out that as long as you have some kind of energy and it creates gravity, everything bends around it. It doesn't matter what it is made of, all things. This is sort of what Einstein called the equivalence principle, if you're familiar with it. Another question is, well, what has NASA done really related to black holes? Did they ever send probes to black holes? How many people think it's true that NASA has sent probes to black holes? You get the skeptic again. All right, how many people think it's false? Okay, you guys are pretty smart, actually. So yeah, of course, we haven't sent anything to black holes. And really, the reason is because they're just so far away. They are millions to billions of light years away. And there's nothing we have that can reach there. I'll talk a little bit about possibilities of how we can reach there later. What about this? This is a little strange. NASA monitors black holes. Why would they do that? That's kind of, who cares, right? How many people think that NASA monitors black holes? Okay, how many people think it's crazy that NASA would spend money on black holes? Okay, hey, that's great, you believe in it. So yeah, it's actually true. NASA's always monitoring black holes with many different telescopes all over the world, in space, constantly, throughout the entire universe. It's a very impressive set of arrays that we have that monitor black holes. The reason why black holes are so interesting, the reason why we spend money on it, is because they're so bright. We can see them throughout the universe. And I'll talk about that a little later. How about this one? Sounds a little fishy. Our galaxy center, or the center of our galaxy, has a giant black hole. How many people think that's true? How many people think it's false? Sounds crazy, right? Okay, well, it's actually true. And you guys are pretty smart. So it turns out that I'll talk about it later. Our galaxy center has a huge, massive black hole. How about this? Nothing escapes a black hole. How many people think that's true? It looks like we kind of got a near split. How many people think it's false? How many don't know? That's a good question. So it turns out this is false. And it looks like it wasn't totally unanimous, and that's good. It turns out that there's a difference between what we say is the black hole and the next thing, which is called the event horizon. How about this? Nothing can escape the event horizon. How many people think that's true? Okay. How many people think it's false? Oh, a lot of people don't know, I can see. So it's actually true. So the black hole then, as clear from these true and false statements, is not just the event horizon. There's more to it. And it turns out that that more to it has something to do with when you rotate a black hole. And I'll talk about that a little bit later. Turns out that that rotating energy is actually outside the event horizon. And that's one of the key points of this talk. How about this? This is really crazy. Black holes can evaporate. kind of like evaporating water. How many people think that's true? All right. How many people think it's false? Crazy idea. Okay, good. So it's actually true. Now, how does this work? Well, it turns out that there's a way in which you can combine, in sort of approximation, Einstein's relativity on one hand and the so-called quantum mechanics on the other hand. And when you do your best, we can't do this completely right now, but if you do your best job at it, it turns out you can show that black holes will eventually evaporate. And it has to do with those merging of the two different physics. In Einstein's relativity, they would not have evaporated. How about this? The Large Hadron Collider will create black holes and destroy the Earth. Now, just want to say, the Large Hadron Collider is a collider that collides protons in Geneva, near Geneva, Switzerland. And it's been sort of sometimes in the news, in the media, as a controversy because maybe it will actually, when it collides those protons, has so much energy, it'll create a black hole, it'll drop down into the planet and start chewing away. That doesn't sound like really nice of the black hole, but still, the question remains, what will actually happen? How many people think it's true that we'll be destroyed by black holes created by the LHC? Oh, I got some doomsdayers out there, okay. How many people think it's false? Okay, you're actually right. Now the trick here, the reason why it's false, is not because we study with a pen and paper about all the different calculations. If you're a particle physicist, that's what you would do. But as an astrophysicist, you look up. You look up and you say, well, there's constantly the same kind of events that they are doing in the LHC hitting our Earth, our planet, all the time, in even higher energy. And there are also other stars in the universe that have the same events hitting them constantly. If it was true that that would create black holes and destroy the Earth, it would have already destroyed the Earth and all those other stars. So I think we're safe. Okay, now the next big idea about black holes I want to talk about is how we can destroy SLAC. And the idea is that the following I want you to get across is that black holes are actually extremely simple. The main thing about black holes you have to appreciate is they're not like any other kind of star in one way. They're simple. They're simple because they only have two properties really in nature. They have a mass, how heavy they are, and they have their spin, how much they rotate. And that's it. That's really all you have to know. You don't have to know how bright they are, what their chemical composition is, nothing. Once you go into the black hole, you no longer need any other information. So that's great.
Don't they have charge?
Yeah, that's why I said in nature. It turns out in nature, the charge doesn't matter. Good question. So now, how can we appreciate how big a black hole is? Well, I have here SLAC. This is the Stanford Linear Accelerator. You're here. Now, what happens if we had a black hole where we took our sun and just compressed it into a black hole? What would it look like? How big would it be? Well, it'd be like that. And I sort of warped it with Photoshop. It's not real. So it turns out that a one solar mass black hole, if we took our sun and we made it into a black hole, will have a 1 mile radius. So that's actually pretty easy, right? So for every mass, solar mass of a black hole, it grows by 1 mile in radius. And for those of you, maybe the younger people don't know about radius, radius is just the distance from the center of the circle to the edge. So that's pretty neat. Well, it turns out that in nature, there really aren't one solar mass black holes. The typical minimum is about 10. So here we have, again, Palo Alto and the Stanford Linear Accelerator, and we're here. How big would that be? How big would 10 solar mass black hole be? It'd be about this big. So that's pretty big. Now remember, think about this. This really means that black holes are extremely compact. We've taken 10 of our suns, squished them down, and they're only as big as not even San Francisco. Well, that's pretty compact. And that's the reason why they're so bright in the end. It's because they grab so much, so close, and can do so much to it before things finally fall in. There's actually a close cousin of black holes that I want to mention because it'll come into the talk later. These are called neutron stars. They're almost a black hole. When they formed, they almost created a black hole. And they're almost as compact as a black hole, but not quite. What is a neutron star? Take an atom like this. It's about an angstrom long. And consider the electrons around the nucleus of the atom. The electrons form kind of a fuzzy ball. And there's a lot of empty space there in terms of how the electrons take up space. What would happen if we took all those electrons, say each one of them, and merged it with one of the protons inside the nucleus? We would get a neutron, it turns out. And if you did all that to all the electrons and merged all the electrons into all the protons, you would get a bunch of neutrons, and you would have removed all the empty space. Once you can do that, suddenly everything collapses, and it's all just a bunch of neutrons everywhere. And this is why neutron stars are so compact and dense, but still normal matter, kind of. And that is because you've removed all the empty space in our atoms. So how big would a neutron star be? So here we again have Palo Alto. Neutron star is not black, like a black hole, and it would be about this big. This is a typical type of neutron star. It's about 1.4 or 1.5 solar masses. So it's like we took our sun, multiplied by 50%, and that's our neutron star. It has about 7-mile radius. So clearly it's not as compact as a black hole, but it's still interesting. So now we're going to move on to the real monsters in the talk, black holes that are huge. And to give us an idea of how huge they are, here's our solar system. We start at the sun, and every time we take a jump, we're actually going a factor of 10 extra in distance. This is what we call a logarithmic scale. And these numbers here represent the astronomical units involved. So we have Earth at 1 AU by definition. We have Saturn at about 10 AU. And this is where the wind from the sun interacts with the interstellar medium around our solar system. And this is about 100 AU or so. Now, to get into one more last thing. One of the closest stars to us is way out here at about 10,000 AU or 100,000 AU, and it's about 4.4 light years away. It's equivalent. So to get an idea of how big black holes are, let's go back first to the biggest star in the universe that we know of. This was VY Canis Majoris. It's 100 solar masses. It's very far away, but it actually is so massive that it reaches all the way to Saturn. So this is a pretty big star. We wouldn't want it around. Now, it turns out that one of the black holes I'll talk about, M87, the system M87, has a 3 billion solar mass black hole. You've taken 3 billion of our suns, compact them up, and it's only reaching Neptune. So we've taken all that space, it's kind of like a small galaxy, into the space of Neptune's orbit. It's a huge amount of mass here. But this is not really the biggest monster. It turns out it's the closest monster, so it's kind of scary because of that. But it's actually not the biggest monster in the universe. Just recently, maybe last year, the biggest monster is called, they just have a funny name for it, it's not really meaningful, Quasar OJ287. It's not O.J. Simpson, trust me. So it turns out that it's 18 billion solar mass black hole. And this is the largest black hole we know of in the entire universe. And it's 3.5 billion light years away. So these are really big black holes. Well, okay, you say, well, okay, yeah, John, that sounds really fun and all, but do we really believe it? Well, okay, there's actually some really hardcore scientists that have been studying this for a while. And they made a bet with each other. Stephen Hawking, who you probably all know, I'm sure, and a guy at Caltech named Kip Thorne, who is a close friend of Stephen Hawking, made a bet. Said, okay, I bet, so Stephen Hawking said, I bet black holes don't exist. You might think that's kind of funny, right? Because he wrote a book about black holes, and he did a lot of research on black holes. But his point of view was that, well, I've done so much work on black holes, if I lose the bet, at least I win something, right? So, okay, it turns out that Kip Thorne voted for black holes. Now, what did they do? They did this back in 1974. Here's the bet. You can read it if you want, or you can ask about it later. And the system that they bet on was so-called Cygnus X1. I'll talk about it a little later, but it's basically a system where there's a central neutron star or black hole, they didn't know, surrounded by some gas, and the gas is coming from a companion star. They call it a binary system. So it turns out that the reason why it's hard to tell the difference between neutron stars and black holes is because you really don't know anything about it except for how Kepler's laws work, the orbiting laws. So the idea is that Kepler's laws tell you about the mass of the object. But what about the mass? Well, it turns out that neutron stars can't be any more massive than about 3 solar masses. You can prove it, and it's a very good estimate. So that means if you find something using Kepler's laws, orbiting laws, that is bigger than 3 solar masses, check mark, you got a black hole. And so they did that. It turns out that it was hard at first and back in 1974, but by 1990, Hawking finally conceded. There were better measurements that actually constrained that object, and it had to be something like 10 or 15 solar masses. So we knew it couldn't be a neutron star. So that's great. So that means that these guys both believe in black holes. If they believe in black holes, it's OK for you to believe in black holes. So now what I'm going to do is I'm going to zoom in. I'm going to start at the largest structures in the universe, go down to our own galaxy, into the center of our galaxy with the stars orbiting the black hole, all the way down to the central black hole. I don't have any t-shirts for sale, sorry. And then finally, actually all the way to the singularity itself, the singularity inside the black hole. So the visible universe is this. But what do I mean by the visible universe? It's about 46.5 billion light years across. You're at the center in the so-called Virgo cluster, supercluster. In the visible universe, I'm not going to talk about the Big Bang Theory and all these kind of things. Only thing you need to know is at some point in the universe, there was a moment when light started to shine, when stars were first born. So there is a time it took for those stars that are far away for the light to eventually reach us. That's why we look like we're in the center of the universe. We're at the center of the visible universe because it takes light time for it to reach us from farther and farther away. Eventually, this will get bigger as time goes on. So what's interesting about the visible universe? Well, one of the interesting things is that even in the visible universe, even at these scales, we can still see events. One of those events is called a gamma ray burst. Gamma ray bursts are one way where black holes are born. In some sense, they're called the birth cry of black holes. What is a gamma ray burst? Well, it's basically, observationally, it's when you see a beam pointed at you of gamma rays lasting seconds. That's the observational fact. And it turns out that we believe that most of the time it's due to a very massive star, something like Betelgeuse or something even more massive, with 30 solar masses in mass, and it dies, it collapses. We see them about twice per day in the sky, all over the universe, all the way to the visible edge of the universe. So let's watch a movie of this process.